Hello all, welcome to discussion on electrodynamics. So in this small video, I'll be discussing the Maxwell's equations in matter. Okay, so we have already derived the Maxwell's equations in free space. It is outside the matter. So the Maxwell's equations outside the matter, we can write del dot E equal rho by epsilon 0, del dot B equals 0, and del cross E equal minus dot P by dot T, and finally del cross B equal mu 0 J plus mu 0 epsilon 0 dot E by dot T. Okay, so this is the Maxwell's equations in free space. Okay, now what would be the difference when you're going to discuss the Maxwell's equation inside the material? So if you consider a material, okay, any material, electric or magnetic material, so any material. So if you consider material, it will contain very large number of charges. Okay, so there may be the free charges and as well as the bound charges. So that is one issue here. Okay, so in case of material, there will be the nucleus and the electron surrounding it. Okay, so there will be atoms, molecules, etc. Now, if you apply the electric field or magnetic field, what would happen? So in case of material, if you apply the electric field or magnetic field, what would happen? So the application of electric field will produce the electric dipole moment here. There will be induced dipole moment, and the application of magnetic field will produce the induced magnetic moment, etc. So that will leads to the creation of additional charges and additional the currents, and they are called bound charges and bound currents. Okay, so we know that the application of electric field produce bound charge. The bound charge is written as rho b equal to minus del dot p, and similarly there will be bound currents. Bound current jb equal del cross m. Okay, now addition to this bound charges and bound current, there will be an additional current. Okay, and that current is called polarization current. So I will just explain what is that. So on the application of electric field, okay, better I will just delete what we have drawn here. Okay, so if there is no field present, if no field, then there will be atoms. The center of the nucleus and center of the electron cloud would be almost same, and there is not be any dipole moment. Now, if you apply the electric field to the system, what would happen? So if you apply the electric field, so what would happen is the positive charge will slightly move towards right, and the electron cloud will shift towards left. So that will leads to polarization P. Okay, so this each atom will dilate. Positive charge, negative charge will be get separated. Now this separation of charge will lead to a small current. Okay, so on the application of electric field or on the application of time varying electric field, there will be a small movement of the charges towards right or left depending upon the direction of electric field. So this will leads to a small current to set up dipole or polarization. Okay, so in order to set up the polarization or in order to set up the induced dipole moment, there will be a small current. Now that small current is called dipole current. Sorry, the polarization current. So we can find its expression. Okay, so in case of if P is a polarization, then the surface charge density sigma P is given by P dot N. Then current is you should write dq by dt. So this we can write as d sigma P by dt into dA. But sigma B is the current, the surface charge density. Sigma B is the surface charge density. So the sigma d sigma B by dt we can also write as dP by dt into dA. Now this dP by dt takes the form of current density. Now this current density we can call it as the polarization current density, and I will denote by symbol Jp. So the polarization current Jp is equal to dou P by dot T. Okay, so apart from the free space, if you are going inside the material, there will be polarization P and magnetization M. The polarization is dipole moment per unit volume, electric dipole moment per unit volume, and magnetization is magnetic dipole moment per unit volume. So due to the presence of polarization, magnetization, inside a material, we'll have additionally is volume charge density rho b is equal to minus del dot p, and additionally there will be two extra current. One is the bound current. So this we have already derived its expression in the last module in the while we are discussing the magnetostatics in matter. And apart from that, there will be an additional current. It's called polarization current. This polarization current would be very small current, but that will also be present when we have the application of the external electric field, because when if you apply the external electric field, there will be the motion of charges in order to set up the polarization or the induced electric dipole. So that will lead a small current. So that small current is called the polarization current Jp. Okay, so the J which is over here is not now it will comprising of three current. One is free current. So J now it will be the sum of the free current plus bound current plus the polarization current, and the row which is coming over here will contain two quantity, the free charge and as well as the bound charge. Okay, now we can substitute it, this expression over here, then we'll see what we'll get. So del dot E is rho by epsilon 0. That would be equal to rho F plus rho B by epsilon 0. Now rho F plus rho B is minus del dot P divided by epsilon 0. So if you just rearrange it, we'll get del dot epsilon 0 E plus P equal rho F. Now this epsilon 0 E plus P is also called the electric displacement. So hence we'll get the equation del dot D equal rho F. Okay, so this expression is already familiar to us. We have already derived it when we're discussing the electrostatics in matter. So there is not much difference. We are getting the same equation del dot D equal rho F. Okay. Now the no modification is required for the second equation when you are going inside the material also, because there will not be any magnetic charge, and no additional change required in the third equation also. So we have four equations here. 1, 2, 3, 4. So no changes required in 2 and 3, because the presence of material does not make any change in equation 2 and 3, because there is no magnetic charge and there is no magnetic current, so there no changes. Okay, but there will be change in the fourth equation. Del cross B now become del cross B is mu 0 J plus mu 0 epsilon 0 dou E by dou T. So this become mu 0 JF plus JB plus JP is mu 0 epsilon 0 dou E by dou T. So this can be written as is equal to mu 0 JF plus what is JB? JB would become del cross M and JP dou P by dou T plus epsilon 0 dou E by dou T. Okay, we can take this mu 0 to the left side and del cross M to the left side. So this I can write del cross B upon mu 0 minus M. That would be equal to, so JF would be there, JF plus these two equation can be combined, dou by dou T of epsilon 0 E plus P. Okay, now in the LHS, what is the quantity inside the bracket? This we have already defined as H, and this epsilon 0 E plus P, that is already known as D, electric displacement. So hence our equation become del cross H equals JF plus dou D by dou T. Okay, now this equation now become very simple. Okay, now we can just summarize the Maxwell's equations in matter. So the Maxwell's equations in matter or Maxwell's equations in material. We have four equations now. One is del dot D equal rho F, del dot B equal 0, del cross E equal minus dou B by dou T, and del cross H equal JF plus dou D by dou T. Okay, so now if you look at the last equation, the del cross H is JF plus dou D by dou T. So dou D by dou T is equivalent to some kind of current. So this dou D by dou T is usually called a displacement current. It's known as displacement current. Now, what would be the expression for displacement current if there is no material? So if there is no material, then polarization would be 0. Then D would be simply equal to epsilon 0 E. Then the displacement current would be equal to epsilon 0 dou E by dou T. Okay, so why I am writing is sometimes they may ask about displacement current. So displacement current usually it is dou D by dou T, and in the absence of material, the displacement current can be written as epsilon 0 dou E by dou T. Okay, so its relevance would become very clear if you look at here. So it is, we have mu 0 J plus mu 0 epsilon 0 dou E by dou T. So I can write it as mu 0 in common J plus epsilon 0 dou E by dou T. So this epsilon 0 dou E by dou T is nothing but a current, and that current is called displacement current. So if the question is some electric field will be given, and if they ask to find the displacement current, we have to just measure, or we have to just calculate epsilon 0 dou E by dou T. So that's it. So that is why I have just mentioned it. Okay. So epsilon 0 dou E by dou T or is called the displacement current if there is no material present, and if material present, the displacement current is dou D by dou T. Okay, so that's all now. Now we can have one more step. We can write this equation in integral form also. So this is the differential equation. So what would be the Maxwell's equation in matter in integral form? Okay, so we can just integrate the first equation over the volume. Then you'll get del dot d d tau equal rho f d tau. So that using divergence theorem, you can convert that into surface integration. So the cross integral d dot ds equal to qf. So that would be the integral form of the first equation. And what would be the integral form of second equation? It would be cross integral b dot ds equal to 0. Okay, I will just show how to convert this differential equation into integral equation. So if you look at del dot d equal to rho f, just integrate it over the volume. Del dot d d tau equal integral rho f d tau. Just integrate it over the volume. Now del dot d d tau can be converted into a surface integration using Gauss's divergence theorem. Okay, so if you, this volume will have some surface, cross surface. So the volume integration of a divergence is simply equal to the surface integration over the cross surface of that integrand d. Now integral rho f d tau will give the total charge qf. So that is the first equation. And second equation, since the right side is 0, you will get the integral del cross integral b dot ds equal to 0. And what about third equation? The third equation would give the closed integral e dot dl equal. It is already known to us. It is nothing but the Maxwell's equations. Sorry, the Faraday's equation. So we can write this equal to minus d by dt integral b dot ds. Okay, so we have to just integrate it over a surface. Integrate over surface, we'll get minus dou by dou t of integral b dot ds. Now the left side integration, the surface integration of a curl can be converted into a line integration. Okay, so that steps, if you want that steps, we can write here. Integral del cross E dot ds equal to minus dou by dou t integral b dot ds. Okay, so just taken the surface integration on both sides. Now the left side can be converted into a line integration using Stokes theorem. And here we have used the Gauss's divergence theorem. Equal to minus dou by dou t integral b dot ds. Now what would be the last equation? If you convert the fourth equation into integral equation, you will get the closed integral h dot dl equal to the jf. If you integrate the surface integration of jf, you'll get if plus dou by dot t of integral d dot ds. Okay, so that's all about the integral form of the Maxwell's equations in matter. So this integral form we required when you are going to discuss about the boundary conditions. If you want to relate the field over the boundaries, then we have to use these equations. Okay, so for the time being, we can stop it here. In the next class, we'll discuss the boundary conditions of field. Okay, so thanks for watching. We'll see you in the next class.